Greetings everybody, welcome to the latest edition of Conceptual Astrophysics videos. This is a series of videos in which we show how to set up and solve astronomy problems. I'm your host, Dr. Christopher Sorolla. Today we're doing something a little bit different. Instead of calculating specific numbers for problems, I want to do a little bit of a not so in-depth discussion of Kepler's second law of planetary motion. Now, Kepler's second law is typically phrased this way. Planets that are in orbit about the sun sweep out equal areas in equal times. Or another way to say it, it's a little bit looser, is when a planet's close to the sun, it speeds up. When a planet's far from the sun, it slows down. But it still keeps on going. Okay, so, well, what about this equal areas and equal times business? What is that talking about? So let's review a little bit of Kepler's second law, and then I want to introduce the physics reason as to why it works the way it works. So let's imagine you have a planet right about here in an orbit around the sun. And for illustration purposes, I have really exaggerated the eccentricity of the orbit, made it a very big oval in order to show this a little bit easier. Now, in say a certain amount of time, that planet will move from say here to here, like that. Now, the rule or the idea for Kepler's second law is take a line that you draw from the sun to the planet, like this, and then draw it again this way so that you've made a little wedge-shaped area, something like that. So there's a specific amount of area inside this wedge during a certain amount of time, okay? Now, let's do that for the same idea, except now we're a lot closer to the sun. So let's imagine the same planet is over here, and in the same amount of time travels over to here. Again, same idea. Sketch line segments between the sun and the planet, and then go ahead and ask what kind of wedge-shaped area you get there. Now, the wedges will be different shapes, obviously, but the areas are identical, okay? And so Kepler knew this, or he discovered this and published his results in 1609. So we've known about this for 4+ centuries now. But where does it come from? Kepler did not really have a good understanding as to why this happens. Well, it turns out it involves an idea called angular momentum. So let's talk about angular momentum a little bit. So angular momentum in physics uses the symbol, or can use the symbol, capital L. Don't worry about it for the moment as to why it's an L. I'll just simply say that the letter A is used for other things, so angular's out. And the letter M is used for other things, like masses, for example, and that's also gone. And it's just one of those deals where astronomers and physicists are looking for something to stand for this quantity, and they landed on L. Otherwise, it's not of our concern, but it is worth mentioning so that we understand that there is a reason. It's just maybe not the simplest one that you can see for yourselves. Anyway, L for angular momentum, like that. Now, what is an angular momentum of an object in orbit like this? So we're going to pretend, for our purposes here, that the planet or moon or asteroid or comet or whatever it is a point-sized object. They aren't, of course, but compared to the distances, even the closest ones are to the sun, it's very tiny. So we can assume that the object itself has no size, but it does possess a mass. And for an object, an individual object that's in a loop, the angular momentum formula turns out to be m times r times v. So what are these things? So angular momentum L, m is the mass of our object, r is the radial or straight line distance from the sun. So let's write that out. So one of these lines, for example, going from the sun to the planet will be little letter r. And v is the velocity or speed of our object. Now, if the object is far away, say if we call this situation number 1, like that, then I would have L equals m r1 v1. For example, r1 would be the distance from here to here, like that. v1 would be the speed at any point, called v1. And so r is very large, v is very small. M I don't have to put a subscript on because it's the same object all the time, right? So I don't have to do that. On the other hand, over in this side of the orbit, notice that the R, I'll call it R, this will be the situation number 2. Notice it's not planet number 2, right? It's just the same planet, it's just in a different spot. So in spot number 2, or section number 2, we'll have an R2 here for the distance from the sun to the planet, and the speed at any given point might look something like that. So the object is going faster when it's close to the sun, right? But it's also a lot closer. And turns out that this idea is kind of an interesting idea. The total, now not the individual parts, because R's and V's are changing constantly as an object is orbiting the sun, but the totals are the same. This idea is called conservation of angular momentum. This is a common enough occurrence in physics, where some quantities, some ideas are conserved under certain circumstances. And so if it's just a planet orbiting the sun and there's nothing else to affect its motion, there's no outside force, say, that comes along and messes it up, this number stays the same, right? There's also things like conservation of energy, which you've probably heard of, and conservation of momentum or linear momentum, and so on and so forth. So these are ideas that are known pretty well in physics, and planets obey these pretty well when orbiting the sun. So this number L, in other words, for any individual object is a set number. Now, that doesn't mean it's the same number for every object. That's not what I'm saying. What I'm saying is that, for example, let's suppose this was the Earth. L is the same for the Earth no matter where it is in its orbit. If this was, say, Pluto, then L is the same number for Pluto no matter where Pluto is in its orbit, and so on like that. So for any individual object, L remains the same, or what we call a constant, right? So that's one thing to talk about. Second thing is, well, let's discuss what speed means, actually. What is a speed anyway? Okay. Well, speed is a change of distance over a change in time, right? So how far do you go divided by how long does it take you to get there? And so a speed, like v, can also be written this way. And let me tell you what the symbols stand for. So little t for time. So t stands for time. That's not too hard to understand. But what about this little triangle here? So this triangle is the capital Greek letter D, or delta. And so, for example, if you have heard of a river delta, I'm sure you have, the reason they call the outlets of rivers, say into a lake or the ocean, a delta is because towards the very end, right before a river tends to drop off and exit into, say, the ocean, it fans out in a triangular shape. So delta, river delta. That has nothing to do with our delta here, unfortunately. This delta refers to change. How have we changed something? Specifically, the final minus initial. So if I say delta R, it is a final position minus an initial position. So where it ended up compared to where it started, right? Now, for our purposes here, we'll assume that delta R is relatively small. You can see, for example, way over here, it's kind of obvious. This right here would be delta R, like that, okay? So with that in mind, let me sort of re-sketch this just for this individual section of it to show it off. So let's put the sun here, the planet right here for starters, and the planet here for finishing, right? So for this small amount of the journey, looks like this, okay, for our R's, this R will be the same value. We'll assume that these R's don't change much from here to here, so that'll be about the same. But there is a definite change in position, which we can call delta R, like that, right? Now, if you look carefully, this looks like a familiar figure. It's called a triangle, right? Never mind my squiggly drawing. If I do a better job, those will be perfectly straight lines. It's obviously a triangle, right? So that's something to bear in mind what we've got here. So we have a triangle, and we could talk about the area of a triangle, right? So it's something to have in the back of our heads. Okay, so these two ideas, the area idea here and the speed here, let's put them together. So L equals mRV in general terms for our planet. Let's replace our V with our delta R over delta t like this. Okay, so notice how this is happening here. All right, now, it turns out that when you have this kind of symbols here, they're all numbers, regular old-fashioned numbers, and we can move them around a little bit to our heart's content. And so let me go ahead and do that. I'm going to take the m and isolate it here. We'll put an r and a delta r together for the moment, like that. I'll have a delta t underneath it there. Then, if you remember the area of a triangle formula, let's write that down for ourselves here. Area of a triangle is 1/2 base times height, right? Or in our picture, 1/2 times r, the height, if you will, multiplied by the base, delta r. By the way, does it matter which one's the base and which one's the height? Not really. It's just a way of speaking. Okay, well, let me go ahead and do something kind of weird. Let me go ahead and put some 1/2s in here. Now, if I put a 1/2 here on top and I divide by 1/2 here on bottom, I haven't changed anything, right? I've made some weird introduction of the number 1/2, but I haven't changed anything because, as we all know, if you divide a number by itself, that equals 1, and the answer you're talking about is not changed, okay? Why would I do that? Well, then I have this 1/2 here would be on the bottom, so m over 1/2 like this. I'm going to leave it, it's going to look weird like that, but I'll leave it there for the moment, okay? Then multiplied by a 1/2 r delta r over delta t over here, and of course that's still all equal to L like that. All right, so I've got these sets of things so far. Why do this? Oh, check it out. 1/2 r delta r is the area of our very skinny triangle. So I have an m over a 1/2, like this. Now, an area of our triangle. So, area, or if I'm being very careful with this, because this is a changing thing, I put as a change of area to be a little cautious about it, and a delta t right like that, okay? Last math trick, okay? Let's take the m and the 1/2 and move them over to the left, which means I divide both sides by the mass, and I multiply both sides by the 1/2. So on one side, I'll have a 1/2, an L, and an M, okay? On the other side, I've left alone the A and the T, like this. They're still there, okay? What's up with this then? What am I doing? Okay, so if we look at this, 1/2 L over M, well, 1/2 is just a number. We made the argument before that this L represents the total angular momentum of our object doesn't change. That's a rule of physics. And the mass, well, it's the same object, so the mass of the object isn't changing either, which means all of this stuff over here doesn't change, which in physics and astronomy we just call a constant. So there's a constant number over here. But then check it out. Area and time. The planet or object sweeps out equal areas in equal amounts of time. And so this is a very abbreviated version of a derivation, or an argument at least for. I've kind of skipped a few steps and shaded a few things, but to get across the basic idea. But this is a way to sort of understand, where does Kepler's second law comes from? It comes from ultimately this idea here, conservation of angular momentum. The fact that the object is orbiting the sun and that particular number doesn't change can be re-expressed as the way that Kepler talks about it here. All right, this has been Conceptual Astrophysics Videos. I am your host, Dr. Christopher Rolla. As always, thanking you for your attention, folks, and clear skies.